All right, this next series of slides has to do with the factors that affect human population growth, but I also have thrown in some information about global warming here, or climate change, because it's related to human population growth. So if we look at this graph, we see that human population over the last few thousand years has been very slow, and then all of a sudden it takes off. And so the first question here, does this graph show exponential growth? It's hard to see here because this line's going up almost straight, but yeah, it's definitely showing exponential growth, which is that J-shaped curve, right? What limited human population prior to 3500 BC? So 3500 BC is right about here. And that's about when the first green revolution, plowing and irrigation and living in communities and so forth began. Prior to that, what limited human population was the ability to find food. We were hunters and gatherers, and there may have been quite a bit of competition, what might even be considered warfare going on, and also disease. So lack of food, warfare, disease kept the human population low and pretty stable and steady before 3500 BC. After 3500 BC, we have the addition of the ability to grow food and cooperate and live in communities and so forth. But what still is keeping the human population relatively low is disease and warfare, for the most part. And there's a bit of an increase here, and then it goes down, probably due to disease. And the same thing here. This arrow is representing the bubonic plague. So this dip is the effect of the bubonic plague. But then the next revolution really is the development of modern medicine, primarily vaccination. So when vaccination came into play here, now we no longer lose a lot of life due to disease, or many fewer lives due to disease. And then we have the Industrial Revolution, which begins the manufacturing of all kinds of goods so that everybody has everything they need. And then we have the second green revolution that goes along with the Haber process, which is something that I brought up back when we were looking at the nitrogen cycle. This scientist named Haber came up with a process that was able to take nitrogen out of the air and use it to synthesize fertilizer. So once because if you'll recall, nitrogen's a limiting nutrient. So the more nitrogen plants have, the faster they'll grow. And that's what has enabled us to grow the amount of food that we now enjoy, but has also been able to sustain the growth of human population so that it is now 7.5 billion and probably going to be going to at least 9 to 11 billion by the time it levels off. But it will level off. In other words, it will become logistic, and this will become an S-shaped curve at some point for some reason. And because of what we would call a limiting factor, if you'll recall, the question is, what is that limiting factor going to be? Is it going to be disease? Is it going to be food? Or are we going to decide or is it going to be warfare? Or are we going to decide that there's just too many people on the planet and decide to stop having so many children? So any one of those things could lead to the leveling off, and it already has started leveling off. And it's primarily due to the decision that people are making, socioeconomic reasons. An example is that it used to be a good idea to have a lot of children so they could help you out on the farm. Well, now most people don't live on the farm. Most people live in the city, and it's too expensive to have a lot of children. So they make the decision not to. And that's all part of what's known as the demographic transition, which is something we'll be looking at a couple slides from now. When we look at this slide, what I'm trying to get across, I put these graphs together to try to get across the connection between carbon emissions and carbon dioxide concentration in the atmosphere and the average global temperature, how the average global temperature has changed over the same time period. And then if you also throw in the graph that we were just looking at on the previous slide, you should recognize the connection to human population growth. all these graphs look the same. They all show basically the exponential increase in whatever they're showing. So it starts, or it's definitely connected to human population growth, but also the Industrial Revolution. So the development of industry and the ability to grow a lot of food, therefore our population increased, and we started burning more and more and more fossil fuels. So the carbon emissions are all from fossil fuel burning, and therefore we're increasing the carbon dioxide concentration of the atmosphere, which is a greenhouse gas. So it's holding in the heat. The atmosphere is acting like a blanket and holding in the heat. And so the average global temperature has increased. So everything's relatively steady for the same time periods in all of these cases, including human population, until we get to the Industrial Revolution and the exponential growth of human population. And then we see the increase in everything. But there's a causal relationship here. Burning fossil fuels, emitting carbon dioxide concentration in the atmosphere, and the average global temperature. And as you can see, it's going up and up and up, much higher than it has been in the relatively recent past, geologically speaking. So what effect do you think this will have on the distribution of biomes and species survival on the planet? Well, we're already seeing that regions are warming up that weren't as warm before. Really, what's going on is that warm places that are now warm are may become cooler. Places that are now cool may become warmer. Places that are now wet might become drier. Places that are now dry might become warmer. So that's why it's better to refer to it as climate change, because it's not all warming. We're not just simply going to warm necessarily. On a global scale, we are the average global temperature, but more regionally, the climate is just going to change, or simply going to change one way or the other. And that's going to cause a shift. So the answer to the question is that the biomes on the planet are going to shift, and the species that are trying to survive in those biomes are going to need to change their range, their population range, where they live. But the problem is that we have produced barriers to that kind of movement, that kind of change in their range, and a lot of species are not going to be able to move, or they're going to encroach on our space, and we're going to probably kill them to keep them out of our space, which is, historically what we've done. So that's probably going to be the result of the climate change for other species on the planet. So it's going to exacerbate, in other words, make worse the whole problem of endangered species and the extinctions that are happening on the planet. So what's this have to do with species tolerance? Species tolerance refers to the ability of species to tolerate a change, whether it be a temperature change or a moisture change. And so species that are more tolerant are going to do better than species that are less tolerant. And the less tolerant species are the ones that are probably going to go extinct as a result of climate change. An example of less tolerant species would be the polar bear. Polar bears hunt on sea ice, and if there's no sea ice, then they have a difficult time hunting and getting the food that they need. And as we've already seen, the sea ice is melting, and polar bears are encroaching into the towns and villages around the Arctic Circle. So they're trying to expand their range and be able to survive and steal our food because they can't get their own food. And so it'll be interesting to see how that all plays out. But polar bears are definitely endangered due to the warming that we're seeing, especially in the Arctic and the Antarctic. But polar bears don't live in the Antarctic. So the Arctic is warming much faster than the rest of the world, the Arctic and the Antarctic. So like it says here, it's warmed 3 to 4 degrees Celsius over the past 50 years. That's a fast increase, and it's projected to rise 4 to 7 degrees in the next 100 years. And that's going to be devastating to life in the Arctic as we know it now, because there will be no sea ice. I threw in this graph to show the change that has taken place over the last just couple thousand years. And as you can see, the temperature over the last couple thousand years is generally a downward slope. So, and as it says here, it's been decreasing per millennia about 0.2 degrees Celsius each 1,000 years. But now it's going back up. Since the 1900s, it's going back up, and it's going back up rather rapidly and higher than it has been in the recent past, the last 2,000 years. And it's continuing to increase. And part of what we're worried about are some positive feedback loops that might get established and cause what we have been referring to as the runaway greenhouse effect. So that's the idea that when the ice melts, the ice and the snow reflect a lot of solar radiation back out into space. When the ice is gone and the snow is gone, the water is just simply going to absorb that solar radiation that normally would have been reflected, that will cause even greater warming and more ice melt off, which will increase solar absorption more, which will melt more ice, and it's a feedback cycle, a positive feedback cycle that will result in the disappearance of the ice and the warming of the Arctic. Another kind of feedback loop is going on with permafrost, because in the Arctic, permafrost is permanently frozen soil, and it's permanently frozen. In the summer, a couple inches thaws, but under just a couple inches and down many feet, there is permanently frozen soil, permanently frozen earth. And with global warming or climate change, that permafrost is melting, that permafrost is thawing, and that permafrost contains a lot of organic material. And that organic material then, once it thaws, starts to decay. And the decay is being carried out by organisms like bacteria and fungi that carry out aerobic cellular respiration. Therefore, they produce carbon dioxide. They're adding carbon dioxide to the atmosphere. So as more permafrost thaws, more carbon dioxide is being released into the atmosphere, which warms the Arctic more, which causes more permafrost to melt or thaw, which causes more decomposition, which releases more carbon dioxide. So again, it's a positive feedback loop that may lead to a runaway greenhouse effect and a very rapid warming of the Earth. All right, so that's my little aside about global warming or climate change and how it relates to human population. And as I mentioned, human population is really the root of all environmental evil, and this is one of the areas where that is true. So here we're looking at the demographic transition, and you may have studied this in other classes or other courses, but to me this gives us some hope for the future in terms of human population growth, and this also would explain how it is that it's projected that human population growth will slow and level off at some point, 9 to 11 billion. And because you've studied this before, you may have studied this before, you may know more about this than I do, but just very basically, we're looking at 3 stages to the demographic transition, and the transition is from less developed countries to more developed countries, or in other words, more developed countries have a tendency to go through the demographic transition, which slows their population growth. So what we're looking at here is birth rate and death rate, birth rate being the red line and death rate being the bluish line. And the idea is in stage 1, both the birth rate and the death rate are high. But then in stage 2, the death rate goes down, decreases, and the birth rate remains relatively the same, so that means the population is growing. And what I'm suggesting is responsible for that, in part anyway, is the availability of food and medicine, so that and infant mortality would decrease, so the death rate goes down, and the population is growing. And then for socioeconomic reasons, In other words, people make the decision, economic decision, family decision, to not have as many children, and that's when the birth rate decreases, and that would be stage 3. And in that case, the population would stop growing exponentially and possibly level off. And that's what we've seen happen in developed countries, more developed countries, as opposed to less developed countries. But less developed countries are developing, so in time, all countries may end up traversing the demographic transition and slowing their population growth. And that's how global population is eventually going to level off, hopefully. And hopefully it will happen before we're all miserable, or at least people in those countries are miserable. Here we're looking at age structure diagrams, and we're comparing a less developed country to a more developed country, like Rwanda versus the United States. And the idea here is that, in relation to the graph that's on the previous slide, the age structure diagram for Rwanda shows high birth rate and high death rate. So in other words, there are a lot of younger people, and they're having a lot of children, but they're not living very long. So high birth rate, high death rate. And that's what's going on during exponential growth. But then the country may go through a demographic transition, and here we see in the U.S. that both the birth rate and the death rate are low, and so this would be an example of showing logistic growth. So Rwanda is still growing exponentially, whereas the United States has leveled off, would show an S-shaped curve, logistic growth, having fewer children and living longer. And as I mentioned, less developed countries tend to eventually go through the demographic transition, and that's pretty much what we're seeing all over the globe. So if we look at global population, and we project it to 2050 here, this table and this graph, or actually the graph is projecting all the way to 2100, we see, that population is definitely increasing throughout the entire time, but check out the growth rate. The growth rate is decreasing, and that would coincide with the transition from exponential growth to logistic growth and the leveling out of the population on the planet at about somewhere between 9 and 11 billion. And again, who knows?